See, induced EMF by Lenz's law opposes either the growth of current or decay of current in the coil, and that itself, electromotive force is induced in a coil. Have I used external source to get an EMF here? No. Then how did I induce the EMF? If a small current flows through the coil, there is small variation in magnetic flux. Therefore, phi is proportional to I of self-inductance L. That is a symbol for the inductor, coil, representation. Hello students, in my today's discussion on electromagnetic induction, we shall learn a very beautiful, emphatic, interesting phenomenon called as self-induction. Again, a concept which plays a very vital role in understanding the AC inductor circuits. So, without time lag, let us enter into the world of self-induction. Before I can mathematically explain what is self-induction, we will first try to understand the physical meaning of this term, self-induction. Nodi, ಎಷ್ಟು ಬ್ಯೂಟಿಫುಲ್ ಆಗಿದೆ ಅಲ್ವಾ ವರ್ಡ್? self-induction. Inducing by itself, ತಾನಾಗಿಯೇ ಉತ್ಪಾದಿಸೋದು, self-induction. Now, the textual meaning says the phenomenon in which EMF is induced in a coil. See, all through my discussion is to understand ways of inducing EMF in a circuit. So here, the phenomenon or the process in which an EMF, electromotive force, is induced in a coil due to change of current. Very important word. Due to change of current through the same coil is what we call self-induction. Self, by itself, without any external aid, ಯಾವುದೇ ಹೊರಗಿನ ಸಪೋರ್ಟ್ ಇಲ್ಲದೆ EMF ನ ಇಂಡ್ಯೂಸ್ ಮಾಡ್ಕೊಳ್ಳೋದು, ತಾನಾಗೆ ಇಂಡ್ಯೂಸ್ ಮಾಡ್ಕೊಳ್ಳೋದು, that is what is called self-induction. So it is a phenomenon, process where EMF is induced in a coil. How? I will change the magnitude of current flowing through the same coil, hence induce EMF. And this phenomenon is called self-induction. ಅಂದ್ರೆ ಮಕ್ಕಳ, ಒಂದು ಕಾಯಿಲಲ್ಲಿ ನಾನು EMF ನ ಇಂಡ್ಯೂಸ್ ಮಾಡ್ತೇನೆ. ಯಾವ ರೀತಿ ಇಂಡ್ಯೂಸ್ ಮಾಡ್ತೀನಿ? ಆ ಕಾಯಿಲಲ್ಲೇ ಪ್ರಸರಿಸುತ್ತಿರುವ ಕರೆಂಟ್ ಅದನ್ನು ಚೇಂಜ್ ಮಾಡ್ತೀನಿ. ಆ ಕಾಯಿಲಲ್ಲಿ ಏನ್ ಕರೆಂಟ್ ಮೂವ್ ಆಗ್ತಿರುತ್ತೆ, ಫ್ಲೋ ಆಗ್ತಿರುತ್ತೆ, ಅದನ್ನ ಚೇಂಜ್ ಮಾಡ್ತೀನಿ. ಆಗೇನಾಗುತ್ತೆ? EMF ಇಂಡ್ಯೂಸ್ ಆಗುತ್ತೆ. ಅದನ್ನೇ ಸೆಲ್ಫ್ ಇಂಡಕ್ಷನ್ ಅಂತ ಕರಿತೀವಿ. ಬಟ್ ಹೌ ಡಸ್ ದಿಸ್ ಪ್ರಾಸೆಸ್ practically work? Let us understand how EMF can be induced in a coil through the phenomenon of self-induction. Yes. Now, if you observe the slide, there is a coil which is connected to a battery and a tap key. A coil which is connected in series with a battery and a tap key. K is called as a tap key, which actually works as a switch. So understand, students, the tap key functions as a switch. Switch on ಮಾಡ್ತೀವಿ, ಕರೆಂಟ್ ಸರ್ಕ್ಯೂಟ್ ಅಲ್ಲಿ ಫ್ಲೋ ಆಗುತ್ತೆ. ಸ್ವಿಚ್ ಆಫ್ ಮಾಡ್ತೀವಿ, there is no flow of current. Why do I require a battery? Some current has to flow through the coil. I have to apply some voltage. Therefore, I am using a battery. So students, there is a coil which is connected to a battery and a tap key. What is the function of the tap key? It works as a switch, allow or block current in the coil. What is the function of the battery? It will actually apply voltage in the circuit. Now, when the key is pressed, or I can also say when it is closed. Now, before I switch on the key, before I press the tap key, there is no current in the circuit. Why? The circuit is open. There is no flow of current. The key is open. Now, when the key is pressed, what happens is, slowly the current rises from 0 to a maximum value. ನೀವು ಕೀ ಪ್ರೆಸ್ ಮಾಡೋಕ್ಕಿಂತ ಮುಂಚೆ, what was the magnitude of current in this circuit? 0. There was no current flowing through the circuit. But the moment key is pressed, andre key na close ಮಾಡಿದ್ರೆ, circuit close ಮಾಡಿದ ತಕ್ಷಣ the current increases slowly from 0 to a maximum value. Andre, that means there is some growth of current in this circuit. current goes on increasing in this circuit. Idina growth of current ant karitivi. Now what happens is, this increasing current changes the magnetic flux that is linked with the coil. Nodi, ಎಷ್ಟು beautiful ಆಗಿದೆ. Current is slowly growing across the coil. The current is slowly increasing across the coil. And what is this increasing current doing? It is changing the magnetic flux linked with the coil. Hence, magnetic flux is changed and EMF is induced in the coil. Nodi, have I used external source to get an EMF here? No. Then how did I induce the EMF? Sir, you changed the strength of the current in the coil. Magnetic flux was changed. EMF was self-induced. So very clearly you observe the current that is growing in the circuit, the current that is increasing across the coil, that itself is changing the magnetic flux linked with the coil. Magnetic flux has changed. EMF is induced. It is self-induction. No external aid was used. Now, what is the direction of the induced EMF? Lenz's law. The induced EMF should oppose the cause that has induced it. Alva? Lenz's law heltala. Direction of the induced EMF is opposite to its cause. So which was the cause here? Increasing current, growth of current. So the direction of induced EMF is opposite to the growth of current. Now, the next case, I will slowly release the key. In the next case, I will slowly release, open the key. Here, current has already reached the maximum value. Now, key is released. The current starts decreasing. Adna decay of current ant karitivi. Decay, koltogodu, kammi aagta barodu. So the moment I have released the tab key, key anna open madid takshana, circuit is open. So current which had reached a maximum value now slowly starts decreasing. There is decay of current in the coil, which means again this decreasing current, decay of current will again change the magnetic flux linked with the coil. Again, EMF is induced. So beautifully, students, it is self-induction. Either increase of current or decrease of current. Either you increase the strength of current, decrease the strength of current. It will change the magnetic flux across the coil. EMF is induced. So beautifully here self-induction is happening. Therefore we say the property of a coil due to which it opposes the growth or decay of current in it is called self-induction. So I have an alternative definition for self-induction. It is the property of a coil, behavior of a coil due to which it opposes the growth of current or decay of current. See, induced EMF by Lenz's law opposes either the growth of current or decay of current in the coil, and that itself is called self-induction. So my dear students, beautifully a phenomenon where EMF is induced in a coil. How? By changing the current flowing through the same coil. Either you increase the current flowing through the coil or decrease the current flowing through the coil. EMF is induced, and that is what is called self-induction. Now, once we have understood the physical meaning of self-induction, we will now try to understand what is meant by coefficient of self-induction, or it is the mathematical understanding of the phenomenon. Coefficient of self-induction. Now, point number 1. We say the magnetic flux linked with any coil at any instant of time is directly proportional to the current flowing through the coil. Gamna itkeli, the magnetic flux that is linked with the coil, magnetic flux associated with the coil is directly proportional to the current flowing through the coil. If a large current flows through the coil, the change in magnetic flux is more. If a small current flows through the coil, there is small variation in magnetic flux. Therefore, phi is proportional to I. Magnetic flux linked with any coil is directly proportional to the current flowing through it. Or, taking out the proportionality symbol, we write phi equals L into I. Proportionality na tegibekadre constant introduce madbekalva. So phi equals L into I, and that constant L is called coefficient of self-induction or self-inductance of the coil. So the L that I have introduced is called coefficient of self-induction. or self-inductance of the coil. Now, if I is equal to 1 ampere, if the current flowing through the coil is 1 ampere, according to this relation, if I becomes 1 ampere, then phi becomes equal to L. Alva? See, phi equals L into I. If I is 1 ampere current, phi equals L. That means self-inductance of a coil is numerically equal to the magnetic flux linked with it when unit current flows through the coil. So when do you say phi is equal to L? When do you say magnetic flux is equal to self-inductance? When the current flowing through the coil is 1 ampere. Therefore, students, if I is equal to 1 ampere, then phi is equal to L. This is important now. From Faraday's second law of EMI, what did Faraday's second law give us? The magnitude of induced EMF. So E equals minus d phi by dt. See, from second law we wrote E is proportional to d phi by dt. Now I eliminate the proportionality symbol and write E is minus d phi by dt. This negative sign is in accordance to Lenz's law. Now, substituting for phi, phi is nothing but L into I. In the previous slide you saw phi equals L into I. L is a constant. What do I call it as? Coefficient of self-inductance. I take L outside. What remains? Di by dt. Now, if this di by dt is 1 ampere per second, I assume the current flowing through the coil changes at the rate of 1 ampere per second. Di by dt is 1 ampere per second. Then E becomes equal to L. Di by dt unity aitalva. So E becomes equal to L, which means the self-inductance of a coil is numerically equal to the induced EMF. E equals L. Self-inductance of a coil is numerically equal to E. What is E? Induced EMF when the current flowing through the coil changes at the rate of 1 ampere per second. If the current flowing through a coil changes at the rate of 1 ampere per second, then the induced EMF becomes equal to the self-inductance of that coil. Now, the SI unit of self-inductance is Henry. Please to remember, the SI unit of self-inductance of a coil is Henry. When is self-inductance? 1 Henry. If E is 1 volt, induced EMF is 1 volt, rate of change of current is 1 ampere per second, then the self-inductance is 1 Henry. Nenpitkolli, first part of the question paper, 1 mark, SI units are asked. So you may have to write the SI unit of self-inductance, which is Henry. So when is self-inductance 1 Henry? The induced EMF has to be 1 volt. When the rate of change of current is 1 ampere per second, then self-inductance is 1 Henry. Here is a small bookwork for you all. A small assignment where I want you all to get an expression for self-inductance of a solenoid. Moving charges al madudvalva solenoid. Here, derive an expression for self-inductance of a solenoid. I want you all to work it out. These things will help you all to trigger your thoughts. Arrive at the expressions self-inductance of a solenoid. Now, coming to a very important derivation, a 3-mark question usually asked, energy stored in an inductor. Second chapterally, I derived an expression for energy stored in a capacitor. Half CV square. Nenpidya? The same way, now I shall derive an expression for energy that is stored in an inductor. Coil in tartha. Inductor is nothing but a coil. Now, I consider an inductor of self-inductance L. There is an inductor of self-inductance L. That is a symbol for the inductor. Coil, representation, which is connected in series with a battery. So the inductor is connected in series with the battery. Now, when I switch on the battery, what is the consequence? Some potential is applied across the inductor, because of which current flows through the inductor. Battery na switch on madidini. There is some current flowing through the inductor. What will that current do? Self-inductance. Yes. It will change the magnetic flux across the inductor, because of which an EMF is induced. Very good. So, ಏನಾಗ್ತಿದೆ ಇಲ್ಲಿ? Battery is switched on, because of which current is flowing through the circuit. Current is flowing through that coil. So what happens? This current will change the magnetic flux linked with the coil and EMF is induced. And you saw that the induced EMF is given by E equals minus L di by dt. Is it not? So E equals minus L di by dt. What was L? Coefficient of self-inductance. What did the negative sign show? Yes, it shows induced EMF opposes the current which is flowing in the circuit. Lenz's law, accordance to Lenz's law, the induced EMF is opposing the growth of current in the circuit. Now, when I say flow of current, that is nothing but flow of charges. If a charge has to move through this inductor, small amount of work has to be done. Potential chapter alli idinella clear agi odidira. And that work done is given as E into dq, force into displacement. This is the force, EMF, that is driving the charge, and I call the displacement as dq. Now substituting for E, dw is L di by dt. This is nothing but E. Where did the negative sign go? It had only a physical meaning. Lenz's law satisfaction. No mathematical meaning in that. So I've just taken the magnitude E L di by dt into dq. Now you have dq by dt. What is dq by dt? Current. Very good. So W is L di dq by dt, and dq by dt is I. So L, I is nothing but dq by dt into di. Now the total work done, or the work done to get maximum current in the inductor, is obtained by integrating equation 2. So integral dw equals integral L I di. Integration on both sides. Integral dw equals integral L I di. And the limits of integration, before we switched on the battery, current in the circuit was 0. Lower limit. Maximum current is I. Upper limit. So integration is done within the limits 0 and I. Integral of dw, capital W, small amount of work plus small amount of work plus small amount of work will give me total work W. L constant taken outside, integral 0 to I di. Integral I square by 2, and therefore the work done on simplification is half Li square. My dear students, this work done is stored as the potential energy in the magnetic field of the inductor. So whatever work done to maintain maximum current is stored as potential energy in the magnetic field of the inductor. Therefore we write energy stored in an inductor U equals half Li square. Just compare. Energy stored in a capacitor was half CV square. See the comparison. C capacitance, L inductance, beautiful. V potential, I current. So this is the expression for energy stored in an inductor. So hope you have understood the concept of self-inductance. The next session, the same way, I will be discussing the concept of mutual inductance. Until then, I expect you review and recall the previous sessions. Meet you all again. Thank you.